Okay, now we're going to look at viewing the percentile rank and kth percentile when presented with ungrouped frequency distribution tables. So in contrast to previous examples, sometimes data sets can be presented in ungrouped frequency distribution tables instead of listed. So for example, if we have this random variable of customer age, previously in the examples that you've seen, the datums have been presented in the form of a list. So this is an example of what we've seen in previous examples. But this data, instead of being formatted in a list, can be formed in a table format, such as an ungrouped frequency distribution. So you can see each one of these datums is represented in this X column. But instead of, like the number 73 being shown 3 times, it's listed once in the table, but with a frequency of 3 to show that it occurs 3 times. And you can see here, like the value 74, it occurs once in the table, but it has a frequency of 2. So it is very common to see data in this table format instead of in the list format. All right, well, all the examples that we've had so far, have had the data pretty much in a list. This table here that I've presented during previous examples, okay, has 3 rows. The top row is the rank, the middle row represents each datum that was in the data set, and the third row down here is the percentile rank for any chosen datum that we've calculated in the previous examples and think pair shares. But what if the data isn't presented like this or isn't formatted like that, but is instead formatted like a table? So I've already talked about the first 2 columns. For the first column is each individual value of X in the data set. The second column is the frequency for each of those values in the data set. And the third column is cumulative frequency. So cumulative is a running sum. So starting with the first value of X and the first frequency, you start the cumulative frequency with the same value as the frequency in the first row. So we have a cumulative frequency of 1. To get the next cumulative frequency for 71 is you take the frequency of 71 and you add it to the previous cumulative frequency. So we get 1 plus 1 equals 2. Then to get the cumulative frequency for 72, we take the frequency of 72, add it to the sum of all the previous frequencies, which is 2, and 1 plus 2 equals 3. To determine the cumulative frequency for 73, we take our frequency of 3, because there were 3 73s in the data set. We add that to the cumulative frequency up until that point, and 3 plus 3 equals 6. So you can see the cumulative frequency is just adding the frequency of each row to the previous cumulative frequency. So the cumulative frequency is kind of like a running sum all the way down the list. Then one of the other columns we have is relative frequency. And again, this is from a previous chapter. But basically, if you move the decimal point over 2 places for each one of these numbers, that represents a percentage. So the relative frequency of a 72 occurring in this data set is 6.25%. The relative frequency of a 71 occurring is 6.25%, and so on. And likewise, when we did cumulative frequency, where we just kind of added the previous cumulative frequency to the current row's frequency, we're doing something like that, but with relative frequency. So if we wanted to figure out the cumulative relative frequency of 71, we would take the relative frequency of 71 and add that to the cumulative relative frequency in the previous row, and 0.0625 plus 0.0625 equals 0.1250. All right, if we needed to calculate the cumulative relative frequency of 72, it's going to be the relative frequency of 72 plus the previous cumulative relative frequency. Add those two together, and you get 0.1875. And you just keep going right on down the line and fill in the rest of that column. All right, so that's a little bit of a review about frequency distribution tables. But let's now turn our attention to the concept at hand, which is percentile rank and kth percentiles. So notice that the cumulative frequency for each value of x in the table is the highest rank of each x. So what do I mean by that? So to kind of make that point, we'll look at this value of x, which is 73, and look at the rank for 73. The rank could be a 4, could be a 5, or could be a 6, right? But notice over here in the ungrouped frequency distribution table, under 73, we have a cumulative frequency of 6. So this value of 6 coincides with the highest rank of 73. All right, now look at this value of 74. The cumulative frequency of 74 is 8. And 8 is also the rank, the highest rank of 74 in the data set. And if we look at 75, the cumulative frequency of 75 is 13, and 13 is the highest rank of our 75s. So what I'm trying to do here in this statement is to draw a correlation between the highest rank of a value of x in our data set with its cumulative frequency in this table. All right, that's number one. Number two is that the cumulative relative frequency represent the percent of datums less than and equal to each value of x. So, for example, if we look at this percentage right here, 37.50, 37.50 represents the number of datums that are 73 and less compared to the total number of datums in the data set. So 37.5% of the datums are 73 and lower. If we look at another one, if we look at 75, so 81.25% of the datums are 75 and lower. Okay, so this percentage in the cumulative relative frequency includes the number of the value of x here that we're talking about. Okay, but the cumulative relative frequency, which represents less than and equal to, conflicts with the strictly less than definition of percentile rank. So for example, when we calculated the percentile rank of 72, and that was 17, here is 72, and 17% would be right here. it would be between 18.75% and 12.5%. So because of the way we defined percentile rank to mean strictly less than, that means typically the value that we calculate for percentile rank is going to be less than the cumulative relative frequency of that same datum of interest. And you can mostly see that pattern repeated for each one of these other percentile ranks that we calculated for 77, 75, and 74. You can look this up on the table to kind of verify that for yourself. Now, this was the example where the datum of interest was given, and we needed to calculate the percentile rank. But we also had to switch that around to where we were given the percentile rank, and we had to calculate the datum of interest that goes with it. So we had to kind of reverse that process. And in reversing that process, we can see that there's a little bit of a discontinuity here. There's a little bit of a problem. And let's kind of take a look at that problem right now. So here we calculated the 85th percentile, and we determined that the 85th percentile was 77.9. So 77.9 would be somewhere right about here. Right? And 77.9 has a percentile rank, has a percentile rank of 85. And 85 is actually positioned right here between 81.25 and 87.5. So you can see we've got a little bit of a discontinuity from the value of our percentile rank here and the associated datum of interest that we calculated to go with it. All right. And the reason for that is that when we were going in this direction, where we had a datum of interest first, and we were calculating a percentile rank, that comes from this actually being what's called an empirical distribution function, which when you look at a graph of it, it kind of looks something like this, right? Very stair-steppy. Whereas when you're given a percentile rank and you're trying to calculate a datum of interest related to it, the graph of that is actually continuous. So this would be a continuous function. And so it'll look something like that. And so because, the way that I'm teaching it here, there could be a discontinuity such as this. When you're kind of going one way to calculate percentile rank and kth percentiles versus going in the opposite direction. Because we're actually kind of calculating things using two different relationships, we could have some discontinuities like this. Okay. But more or less, we're not going to run into very many of those issues. Okay. So having said that, what can we get maybe just by looking at an ungrouped frequency distribution table? So if we look here at looking at the 50th percentile, So the 50th percentile is where 50% of the datums are less than a certain value. So if we come down over here, we can see that 74 is exactly 50%. So 50% of the datums are 74 and lower. But we want to make sure that we're looking for some value where it's strictly greater than this 50%. So we can't have the value 74. Instead, the value that we're going to have is going to be 74.5. If we look at the 28th percentile, so we're looking for the spot where 28% of the datums are less than a given value. All right, let's look and find out where 28% would be. So 28% would be located right here. So 28% would be between 18.75 and 0.375. And so that 28% would be some value of 73. So our 28th percentile would actually be 73. So you can get some information rather quickly from these ungrouped frequency distribution tables, but you really have to kind of know what you're looking for. Otherwise, you can calculate using the same functions that we used here earlier. You can get that same information from the table as well. Okay. So it's kind of shifting things on me. Let's see if I can get that back. No. All right. So let me know if you have any questions.